learn about magnetism, we're going to observe some simple demonstrations that show what magnetism does. Most of us know that a magnet attracts certain materials. As I bring the magnet near the piece of steel, I can feel a force attracting the steel. Magnets can produce a force. As a matter of fact, the force of these small magnets holds this sign on the steel board. Now, let's try the magnet on these materials. It doesn't attract copper, or glass, or zinc, or wood. In fact, magnets attract only iron and steel and a few less common metals. Now, here is a very powerful magnet. Watch this steel ball closely as I place it near the magnet. The magnet attracts a ball from a distance. We say the magnetic force acts through space. Here's another way to see that a magnet's force acts through space. This bolt is attached to the base of the stand by a thread. When I place a powerful magnet at the top, the bolt is held in space by the magnet's attraction, a force acting from here to here. Without the magnetic force, the bolt falls. To find out more about magnetic force, I'll lay some paper on top of this magnet. You'll see later why I'm using wax paper. When I sprinkle the iron filings onto the paper, the force of the magnet pulls the filings into a pattern. These lines, called lines of force, show the magnetic field around the magnet. Now we'll see why I used wax paper. The heat of this lamp will soften the wax and embed the filings. Now we have a permanent record of the magnetic field. With light behind the paper, we can see the lines of force very clearly. They come from the ends of the magnet and go completely around. The magnetic force extends into space around the magnet. Let's learn more about the force at the ends of the magnet. I'll roll this bar magnet in iron filings. Some are attracted to the center of the magnet, but most of the filings are attracted to the ends. The ends of the magnet, where the force is strongest, are called poles. All magnets have poles. To see more about poles, I'll use this magnet, which is hanging, so it can turn freely. After a few moments, it comes to rest, one pole pointing toward the north and the other toward the south. The pole that points north is called the north-seeking pole, or N-pole, and the south-seeking pole is called the S-pole. Here I have a bar magnet that turns freely on a pivot. It has the poles labeled. Now, when I bring two N-poles together, they push against each other. We say they repel. Two S-poles also repel. But when I bring an N and an S pole together, they attract. Let's remember that like poles repel, unlike poles attract. Here I have two magnets that are circular. They have a pole on each side. Let's see what happens when I place them on this stand like poles facing each other. The like poles are repelling each other. The top magnet is held in space by the magnetic force. The force is so strong that it holds the top magnet up. Here are 4 magnets. These two have like poles together, and these have unlike poles together. I'll use wax paper again so we can see the lines of force. The lines of force are forming different patterns. After heating the paper, as I did before, we get a good picture of the lines of force. Between the 2 unlike poles of the magnet, the lines of force join. But between the like poles, we can see that the lines of force do not join. This iron bar is not a magnet. It doesn't attract these steel balls. But when I touch the bar with this magnet, it does attract them. So I made a magnet of the iron bar when I touched it with this magnet. Magnets can make other magnets. But when I remove the magnet, the bar soon loses its magnetism. It was a temporary magnet. To make a permanent magnet, one that will continue to be a magnet, I'll stroke the bar over one pole of this magnet, always in the same direction. Now I'll take the magnet away. The bar lifts the steel balls. It is a permanent magnet. I magnetize this iron bar by stroking it with a magnet. This model will help us see how it happens. In the model, there are many tiny magnets pointing in different directions. They represent the magnetic particles in an iron bar. When I stroke the model with a magnet, all the magnetic particles line up. All the N poles point one way, and the S poles the other. Scientists think that in a magnet, many magnetic particles are lined up. A compass is a very useful device. There are several kinds of compasses. Here's the kind you may have seen before. A compass needle is a magnet. And its N pole points toward the north, and its S pole toward the south, helping us to find directions. A compass needle points north and south because the Earth is a magnet. The compass needle is attracted by the Earth's magnetic poles. The north magnetic pole here and the south magnetic pole here are different from the north and south geographic poles. Since the Earth is a magnet, there is a magnetic field around it. The lines of force extend from pole to pole. We'll use this globe, which has a magnet mounted inside, to demonstrate how we use a compass. A compass needle, which is a magnet, is attracted by the Earth's magnetic poles. It shows us the directions of the lines of force leading from pole to pole. So, magnetism is all around us. Let's remember some of the things we've seen. We saw that magnets can produce a force. Magnets have poles. Magnets can make other magnets. And the Earth is a magnet. By experimenting with magnets, from this simple bar magnet to the Earth itself, we can learn many things about the force we call magnetism.